To investigate associations between variables, one of the simplest metrics to start with is the covariance. Essentially, the covariance tells us if two variables tend to move in the same direction or not. To formally define covariance, let us consider two variables, which we call x and y. The covariance of x and y is given by this expression. And in this expression, capital letter E here represents the expected value or the mean. For example, E of x here is the expected value of x or the mean of x. So what this expression tells us is that the covariance of x and y is given by the expected value of the product of two quantities. The first quantity being x minus his expected value, and the second one being y minus his own expected value. In practice, we observe values of each of these variables. And so let us denote by x1 to xn the observed values of x, and by y1 to yn the corresponding observed values for y. Such observed values can be used to obtain an estimate of the covariance. One of the most commonly used estimates for the covariance of x and y is given by this formula. And this is often referred to as the sample covariance. Sample covariance because it is expressed in terms of the samples of data that has been collected on x and y. And in this sample covariance of x and y, the x with the bar on top represents the average of the observed values of x, and similarly y with the bar on top represents the average of the observed values of y. So essentially what is going on in the calculation of the sample covariance of x and y is that for x we calculate the average and we subtract it from each individual observed values of x. We do the same thing separately for y, and then take the product of these individual differences and sum them over the sample. N here, of course, represents the sample size. One question that might arise is, what does this mean in practical terms, or how do we interpret this in practice? To answer this question, let us consider one of the data sets shown earlier. Here it is. First thing, we calculate the mean or the average of x, the observed values of x, and we draw a vertical line going through it. For this data set, the average values of x is 0. Similarly, we compute the average values of the y's, and we draw a horizontal line going through that average values. For this data, the average values of y is very close to 2. These two lines divide our space into 4 regions or 4 quadrants. We have region 1 here, region 2, region 3, and region 4. Let us focus on region 2 and region 3 first. We would come back to region 1 and region 4 later on. In region 2, any point that we take here, it's clear that the corresponding values of x is larger than the average values because the point is on the right hand side of the vertical line. Similarly, for any point that we take, the corresponding values of y is larger than the average values of y because the points in these regions are above the line going through the average values of y's. As a result, in these regions, xi minus x bar shown here is positive, and yi minus y bar shown here is positive. So this product is positive, right? The product of two positive numbers is positive. Similarly, if we go in this, if we consider this third region, we would notice that this xi minus x bar and yi minus y bar are negative for any of the points that we take in this third region. As a result, the product of these two is positive. The product of two negative numbers is a positive number. So in these two regions, we know that this product, these individual products, are positive. Therefore, in practice, if most of the points fall into these two regions, the sample covariance, the resulting sample covariance, will tend to be positive, because the positive component here coming from these two regions would dominate the negative ones. Of course, we are assuming that for the few points that fall into region 1 and region 4, the individual deviations, these deviations are not extreme. And let us note that when most points fall into regions 2 and region 3, overall we have an upward pattern, right? So if we have to summarize what we have discussed regarding this graphic, we would conclude that the covariance of x and y is positive whenever x and y tend to move in the same directions. Notice that having an upward pattern here basically means that x and y tend to move in the same direction. And similarly, if most points happen to fall into region 1 and region 4, then the covariance would be negative, would tend to be negative. And having most of the point in region 1 and region 4 means that we have a downward pattern. Downward patterns means that x and y tend to move in opposite direction. So covariance of x and y negative means that overall x and y tend to move in opposite direction. What if the data is heavily spread in the fourth region? The data is spread heavily between region 1, 2, 3, and 4. In that case, the covariance would tend to be close to 0, because the positive component in region 2 and 3 would tend to be cancelled out by the negative component from regions 1 and region 4. Therefore, for this slide, we can conclude that the covariance gives us a measure of how two variables change together overall. So far, we have defined what the covariance is, and look at how to estimate it or to calculate it, and explore how it can be used to determine the overall direction of the association between variables. However, the covariance has got some problems. One of the main problems arises from the fact that the covariance is sensitive to scale. For example, if we multiply, let's say, variable x by 10, then the resulting covariance between x and y would also be scaled up by 10. Although this is a nice property from a mathematical point of view, it is not great when it comes to comparing the association or the magnitude of associations between variables. Because what this sensitivity to scales means is that one can simply increase the covariance by scaling up one of the variables. Due to this sensitivity to scale, we need an alternative and better metric that can be used to assess and compare the magnitude of associations between variables. The alternative metric that we would consider in the next few slides is the correlation coefficient.